Second part of the lecture 12, where we will be talking mainly about nanocomposites and the other properties such as interlaminar toughening of composites and things like that. So, what are nanocomposites? Nanocomposites are one in which, there could be more than one type of fibrous reinforcement, where one of those fibrous reinforcements could be in the form of nano-sized particles or nano-sized fibers. And there are many challenges related to these composites, the most important one of which is the fact that you cannot disperse them you cannot disperse these nano-sized particles very well in the composite material due to a number of different factors. Most of it is that they tend to agglomerate and they tend to um, get together in one portion where that extra nano-sized fillers can cause some kind of agglomeration and start the crack or cause a weakening of the material at that point and start a failure at that point due to the excessive agglomeration of these nanoparticles. So that is the biggest challenge with regard to these nanoparticles. But there are several advantages due to these nanocomposites. The most important one is that they could be um, providing extra uh, properties such as barrier properties or interlaminar properties and so on. Okay, so the earliest nanocomposites were based on nanofibers and multi-wall nanotubes or even single-wall nanotubes. People tried not to use the single-wall nanotubes because single-wall nanotubes in those days were like they were about $2,000 a gram. So if you want to add, say, more than 1% or 2% of that in a composite costing about, say, 300 or 400 or maximum $500, you are doubling the cost of that component with just the addition of 1% carbon nanotubes. And does it really result in that much improvement in these properties? Difficult to say. So it was a very big challenge. I don't think that we have still gotten over those challenges, but hopefully they will get over those in the next couple of years at least. People are still working on them, including our group here at Oklahoma State, but not with carbon nanotubes, but with other types of nanofillers. So you can see that these are the very very thin fibers. So this is 10 millimeters. So these fibers are of the order of couple of nanometers. There could be vapor grown carbon nanofibers, but the improvement in properties is not the same as carbon nanotubes. So as I said to you, the material property calculations are very complicated, but the processing is even more difficult. So these are some modeling aspects to the actual composite property measurements, but I'm not expecting you to go over that in great detail. So how do you predict the Young's modulus of elasticity? So uh, you can calculate the effective modulus for randomly oriented nanotubes. They have very complex formulas, but both are functions of the waviness factor. And if you know the waviness factor, then you can kind of calculate approximately the properties, different properties. So the waviness factor the if the waviness factor is 0, you get the best property improvements. And even with 0.25%, so from 2 GPa to all the way to 10 GPa, you can increase that. But most of the time you end up with properties in this range, so you get only an improvement of about, say, 5 to 6%. And why do you want to add double the cost of your component for 5 to 6% improvement in modulus? That's a difficult question to answer. So what people have tried to do is to combine the nanoparticles and conventional continuous fibers. So you fill in the area between the fibers with these nanoparticles. So if you have that, then it makes it uh, easy for you to get better bonding so that the fibers won't be easy to pull off. So you can, so this is an example. So you can calculate that based on the waviness factor. So you can predict the properties based on that. Um, Sorry, there's a spelling mistake here in the shear strength. I was cutting and pasting it to somewhere else, so I didn't notice that. I'm sorry about that. So it should have been STRENGTH rather than HT. So you can predict the properties, but are you going to get those predicted properties? That is difficult to say. So, talking about nano composites, one of the biggest uh, areas where they were expected to improve the properties of composites was in the area of interlaminar strength. So what used to happen was that what happens is that if you have a composite laminate, if you even have a very low velocity impact, it can lead to delaminations. And this is even more exacerbated if your properties are if your properties are measured in the mode 1 um, normal load method. So it's a serious problem. So improved fracture toughness and interlaminar shear strength is desired, especially for mode 1 type of properties. So what people have tried to do is to impede that delamination. They interleave a tough layer between pre-preg plies, like they would put rubber or some kind of an epoxy film between that in order to improve the toughness, or they would put some kind of pins uh, in the rigid cured carbon fiber BMI. So these are carbon fiber BMI resin rods, and they would put that into laid up uncured plies. But even though that can effectively impede the delamination, it can damage the um, damage uh, the in-plane properties tremendously. And so people don't always try this in the traditional sense. So what we tried to do was to add these nanoparticles between the prepreg layers so that you can improve the bonding between those prepreg layers to improve the interlaminar toughness of these composites. So you can add nanotubes or you can add nanoparticles, etc. But most of the time what happens is that with carbon nanoparticles and carbon nanotubes, they have very high surface area, but very poor reactivity and not very high strength. So they do not add anything to the properties by themselves, but they can damage the so they don't always give you the property improvements for the amount of material that you are adding. So people have tried with different kinds of materials like nanoclay, carbon nanotubes, graphite nanoparticles, etc., or POS, etc. But the problem with most of these is that they are not really compatible with the epoxy resin systems. So what we found is that either POS or graphene oxide are compatible with epoxy resin systems or different resin systems, and they have very high surface areas and they give you high mechanical properties. They are also easily dispersible, especially in a polar solvent like even with ethanol and things like that. So they have very good physical and chemical interaction with the matrix resin, and um, so there are many multiple functionalities that you can have in these graphene oxide particles, um, and it will improve the interlaminar properties also. So the reactivity is because of the organic groups, and they contribute uh, to the reaction between the matrix resin and the bonds at the end of the matrix resin molecules. So the biggest contribution is from the carboxylic groups in graphene oxide. Similarly, you can also have polyhedral oligomeric silsexoxane or POS. They also have similar cage type of structure with a lot of reactive groups at the ends. They can react with the matrix resin and improve the different kinds of properties. So these are the types of resin, POS molecules that we selected, and we also used graphene oxide. So we synthesized the graphene oxide by ourselves. This was all done by our group here in Oklahoma State. And we dispersed that in a solution of polyvinyl pyrrolidone. It's a good compatibilizer with resin systems, and then you sprayed that or you painted that on the fabric between the pre-preg layers, and the fabrication process is given here. And what we found is that by adding the graphene oxide or POS to the matrix resin, to the polyvinyl pyrrolidone, we were able to exfoliate the graphene oxide, so it gave us extra surface area for the reaction between the graphene oxide and POS molecules with the matrix resin system. And the fracture toughness is measured by using a process called double cantilever beam. So it is essentially your, I think it might be there. Okay, it's not there. I apologize. You can look up the double cantilever beam testing, and what it is okay. Oops. Okay, yeah, here it is. Yes. So what you do is you put this panel, this sample, and you have some kind of hinges attached to the ends, metallic hinges, and you fix that within the grips, and when you pull that apart, you are looking at how easy or difficult it is for this crack to propagate from one end to the other. And the toughness of these materials is calculated by this equation. And what we found is that if you have the baseline with no additive, it would fracture in a very easy manner. But when you started adding these things, it almost double the toughness of these materials with just 0.02% or 0.2% by weight of the composite by itself. So it's very, very small quantities that you need to add in order to get these improvements. So you can see that it increased by almost 100%. The toughness increased by 100% with very small quantities of the additive. But you could only add very small quantities because more than that it started agglomerating. So what we did was we hybridized these molecules. So we took one molecule of POS and one molecule of graphene oxide and we hybridized them to create a graphene nanoparticle or is grafted natural polymer particle or PGP composites. And in this case, one of the additives was starch. And when you started adding that, what we found is that it started increasing it even beyond 100%. And that improvement doesn't seem to have a limit. So you could probably add more of that material. So all you have to do is to make sure that you have enough of that material to add into the composite system. And the other nice thing is that when you start adding all these things, it starts decreasing the stiffness of your material, stiffness of your composite material. But surprisingly, what we found is that when you start adding these nanoparticles, it does not damage the elastic modulus of the composite material itself. So it means that you get improvement in toughness without damaging the stiffness and strength of the material. What we found is that the addition of these graphene oxide or POS molecules, it starts creating a wavy pattern for the composite failure. Compared to if you didn't have that at all, the crack starts moving without any stoppage of the crack at all. But when you have these nanoparticles, it stops the crack and it adds to the toughening or the interlaminar strength of your composite material. I'm going to jump through these next few slides. I'm not going to talk about that. You can take a look at that if you are interested, but I'm not going to talk about that at all. Okay, so let me talk a little bit about self-healing. So you know that composites are extremely stiff and strong, so they can even be considered to be pretty brittle. So what happens is that if a crack starts, it can easily propagate through the composite material. And in order to prevent that, especially if it is going to happen during service, we create this was originally done at University of Illinois, and then it is even being done at University of Tulsa. So what happens is that you add these microcapsules that release a self-healing fluid that goes into the cracks and solidifies and prevents the crack from propagating further. So let me not go over that. So let's go over composites at different length scales. So you can see that what are the properties that are required, what are the properties that we are interested in. So we are interested in bulk properties when you are going to be looking at big components, but you're also interested in the composite properties at the laminate level, at the micro scale level, etc. So there are many different types of composite materials that have been evaluated. So in this case, these are laminated materials. So you have aluminum and silicon carbide materials. So in this case, the silicon carbide is deposited by um, uh, a deposition process, an electronic deposition process, and the aluminum is by taking it as a substrate. So that can have its own benefits. So if you have these materials, I think we did talk a little bit about this. So if you have that, um, it actually improves the peel strength of this composite material. So we did talk about that in one of the earlier lectures, right? No, probably not. That was for another class. I'm sorry about that. But what happens is that when you have this rubber or the prepreg material and the metal will prevent the crack from propagating through the metal into the next metal layer. And this is a type of a composite that is used in many sound absorption type of applications, especially um, in a big auditorium. Okay, so the side walls are all made out of these materials, and the other advantage is that you can easily replace panels out of that. So you make panels that can easily be inserted into the slot of the wall, and that provides you with the properties that you require, uh, sound absorption as well as toughness of these materials. So let me stop here and I will take this up in the next set of lectures.